Today, we're going to talk about arc length. Arc length is just the length of a curve on an interval. The idea here is that instead of trying to take the length of this whole thing at once, we're going to break it up into straight line segments and then add them up, like here. But now let's examine one of these a little more closely. Let's take a look at this segment right here. So we can break it down into its x and y components like this. And then I'm going to say that this whole line is length ds. And remember, we want to add all of these ds's up to get the length of this line. So we're going to say that L, or the length of the line, is the integral from a to b of ds. But we can't use ds here because it's never given to us in a problem. So we have to simplify it into more elementary terms. Looking at this, we've made a right triangle with the components of ds. So if this is ds, then this must be dx and this must be dy. And then using the Pythagorean theorem, it follows that dx squared plus dy squared equals ds squared. And then taking the square root of both sides, we have ds equals the square root of dx squared plus dy squared, like so. Now we have stuff we can work with, so I'm going to make this substitution into our integral. Now it's a little better, but we can go further than this. I'm going to go ahead and multiply this dy squared by dx squared over dx squared, like this, and you'll see in a minute why I did that. Notice I haven't changed the integral because if I didn't do anything, these would cancel to leave this. So now I'm going to factor out a dx squared inside the square root, like this, and since this is a dx squared inside a square root, we can just take it out, like so. And notice that we have a dy squared over a dx squared, so we can combine that into one squared fraction, like so. And now in this form, the formula is now usable because we're normally given this curve as a function of x. So we have the derivative of the function of x squared in the integrand and integrated with dx. And that's the formula for arc length. This is the arc length formula if you're given a function of x. But if you're given a function of y, then that's no problem. The first example that we're going to do is we're going to find the length of ln of cosine of x. So the first thing we're going to do is we're going to set up our integral, like so. And so we know that a is 0 and b is pi over 3, but we need to find dy dx. So I have y equals ln of cosine of x. And when we take the derivative of this with respect to x, remember that the derivative of ln u is 1 over u du. So in this case, our u is cosine of x, so our derivative is 1 over cosine of x times our du, which is negative sine. And this can be simplified down to negative tangent of x. I'm going to make this substitution into our integral, like so. And now I'm going to apply the square on the tangent x, like so. And now I'm going to call on the trigonometric identity that secant squared x minus tangent squared x is 1. When I add tangent squared to both sides, we get secant squared x equals 1 plus tangent squared x, which is what we have right here. So I'm going to go ahead and replace this with secant squared x, like so. And now the square root and the square can cancel to leave the integral from 0 to pi over 3 of secant x dx. So you'll remember from the basic integrals videos that the integral of secant x is ln of secant x plus tangent x. And we're going to evaluate this from 0 to pi over 3. And this expands like this. Let's go ahead and evaluate this latter term first. The tangent of 0 is 0, so we can just get rid of this. And so the secant of 0 is 1 over the cosine of 0. And we know that cosine of 0 is 1, so this becomes 1. But we also know that the ln of 1 is 0, so this actually just goes away entirely. Now all that's left is to evaluate this. So we have the ln of, so secant of pi over 3 is 1 over cosine of pi over 3. So since cosine of pi over 3 is 1/2, 1 over 1/2 is 2. Plus, the tangent is sine over cosine. The sine is root 3 over 2, and cosine is 1 over 2. So those two divided is root 3. And this is the length of the curve ln of cosine of x on the interval 0 to pi over 3. And for the second example, we're going to find the length of the curve e to the x plus e to the minus x over 2 from 0 to 1. So as always, we're going to begin by setting up our integral, like so. So we know a is 0 and b is 1, but we need to find dy dx. Okay, now we're going to find the derivative of this. And remember that because of the constant multiple rule, we can pull this 1/2 outside of the derivative, like so. Now when we find the derivative of this, we have 1/2 times, so the derivative of e to the x is e to the x. But the derivative of e to the minus x is, well, this is e to the u. So the derivative of e to the u is e to the u du. So we have e to the u, and then du, so derivative of negative x is -1, like so. And we can just make this into the subtraction and get rid of it. So this is our derivative, and I'm going to put that in here, like so. First thing I'm going to do is I'm going to apply the square, like so. And then I'm going to expand the square, like so. And then I'm going to distribute the 1/4, like so. Now I'm going to combine like terms by doing 1 minus 1/2, like this. So now what I'm going to do is I'm going to factor out the 1/4 to what it was before, like this. And so what do you notice here? This inside the brackets is e to the x plus e to the minus x squared. So I'm going to rewrite it as such, like this. And now I'm going to apply the square root, like so. And now we can finally integrate and evaluate. Okay, so this is our result of integration, and we're going to evaluate from 0 to 1. And this expands like so. And you can see that e to the 0 is 1 minus e to the -0, also 1. So this is 0, so this goes away. And so now we're left with this, which is 1/2 times e minus 1 over e. And so our final answer is e over 2 minus 1 over 2e. And this is the length of the curve e to the x plus e to the minus x over 2 in the interval 0 to 1. And this is the end of AP Calculus AB. Thanks for watching my videos. I really do hope they were helpful. But BC students still have a little more work to do.